We simply define that by finite subset. If I have any collection of subsets of a sigma field, we'll call that collection independent if and only if any finite subset of those collections is independent in the sense that we've just given. So one consequence of that, a simple exercise using the continuity of probability measures, is that if I have a sequence of events, a countable sequence, that are independent, then the probability of that countably infinite intersection is the countably infinite product of the probabilities of the events, where that is defined to be the limit as, say, capital M goes to infinity of the product n equal 1 up to m of the probability of an. And that exercise is on your homework. Keeping that consequence of independence in mind, we're now going to finally prove the second half of the Borel Cantelli lemma. Remember, the first part of the Borel Cantelli lemma said that if I have a sequence of events whose probabilities form a summable sequence, then the probability that infinitely many of those events occur is 0. The partial converse of that, part 2 of the Borel Cantelli lemma, is if I have a sequence of independent events whose probabilities are not summable, then with probability 1, infinitely many of those events do occur. Before we prove that, let's look at the example that we gave once before, now having the formal statement here. Suppose that I have a sequence of Bernoulli random variables with some probabilities Pn. For example, Pn equal to 1 over n that form a non-summable sequence. If the events xn equal 1 are all independent, then the Borel Cantelli lemma, part 2, tells us that xn will equal 1 for infinitely many n, with probability 1. For example, if I toss an infinite sequence of biased coins, I hand you the first coin, which has probability 1/2 of coming up heads. You toss it and record the result. Then I hand you a new coin, which has probability 1/3 of coming up heads. You toss it and record the result. Then I hand you a new coin, which has probability 1/4 of coming up heads. You toss it and record the result. And at the end of a very long day, you look at the sequence of tosses. Then with probability 1, you will see infinitely many heads in that sequence, even though the probability of heads was shrinking to 0 as the tosses went on. That's the power of the Borel Cantelli lemma. And we'll conclude this lecture by proving it. Let's just recall this nice formulation for the set of outcomes that occur in infinitely many of the ANs. We take the union past some point k of all of the ANs. In other words, for fixed k, this is the set of outcomes that occur somewhere after time k, and we take the intersection of all of those. So this is the collection of outcomes that keep coming back over and over in the tail of this sequence of events. It's the set of outcomes that occur in infinitely many of the outcomes. Now, note that this union here, which I'll call UK, is a decreasing sequence. As k increases, this is a union of fewer and fewer sets, and so it is a decreasing sequence of sets, and therefore, by the continuity of measures, the probability of this set, which is the set where an occurs infinitely often, is the limit, as k goes to infinity, of the probability of that UK, the probability of the union over n bigger than or equal to k of an. Now I'm going to be sneaky and write that inside the limit as 1 minus the probability of the complement, which is the intersection of the complements. And of course, I can pass the limit through the 1, so that's 1 minus the limit as k goes to infinity of the probability of that intersection of complements. Now let's consider fixed k. That probability of the intersection n going from k up to infinity of an complement. Since the an's are independent, and therefore, as we've now seen, the an complements are independent, this is the infinite product, n going from k up to infinity, of the probability of an complement, which is the infinite product, n going from k up to infinity, of 1 minus the probability of an. How do we handle an infinite product like that? We have many more tools for handling infinite sums. Well, let's turn this into a sum by taking the logarithm. And the nice part here is that we don't really have to take the logarithm because of a nice calculus inequality. Let's call this probability here Pn, which is a number between 0 and 1. So that's a product of 1 minus Pn. And I just want to note that 1 minus Pn is a non-negative number, but it's also bounded above by e to the minus Pn. That's a simple calculus exercise. Consider the function f at p equals e to the minus p plus p minus 1 on the unit interval. Notice that f at 0 is equal to 0, and calculate that this differentiable function has derivative equal to minus e to the minus p plus 1, which is greater than or equal to 0 on the unit interval, because e to the minus p is less than or equal to 1 there. Therefore, this is a non-decreasing function which starts at 0, and therefore it's positive on the unit interval, which is exactly to say this. And so therefore, this product, as you can easily work out using the limit definition, will be less than or equal to the product n going from k up to infinity of e to the minus pn. Well, let's write out what that means as a limit. That is the limit as capital M goes to infinity of the product n going from k up to capital M of e to the minus pn. And now by properties of exponentials, this is the limit as m goes to infinity of e to the minus sum n going from k up to capital M of Pn. Now, for any fixed k, this sum goes to infinity because of our assumption that the sum of the Pn's is infinite. If there were some tail of this sum that was finite, then the whole sum would be finite. So this tends to minus infinity. Therefore, by continuity of exponentials, this tends to 0. In fact, for any fixed k, this is equal to 0 for any fixed k. And so we therefore have that this limit is a limit of a constant sequence. This is 1 minus 0, which is 1, which concludes our proof of the Borel Cantelli lemma, part 2. We'll put the two Borel Cantelli lemma parts together into a single 0-1 law shortly, and study why it is that the outcomes have to be either 0 or 1. But before we get there, in the next lecture, we're going to now talk about independence of random variables.